Okay, since we have to do a whole bunch of stuff, I'll steal a minute. So we can start. Just to review kind of what we did last time, kind of went over the gain derivations for the current mirror-loaded differential pair, and then kind of just started at the very end talking about the unbalanced types of circuits. Current mirror-loaded one was kind of already an implicit example of the asymmetry in the circuit. But then, due to other factors, you can get essentially a full imbalance in the diff pair, and we'll cover some of them today. But really, what we talked about, what that does is kind of look at create this VOS, or the offset voltage, that shifts the transfer characteristics of the diff pair. And we defined that the input referred offset is the point where at the input voltage where the output voltage equals 0. Right? So that was kind of from last time. And today we're going to see some of the physical examples of where the offset comes from. So if you look at offset, we're going to say voltage of. There's two reasons why offset shows up in differential pairs. So one is what we could call a systematic. And this, oops. This happens even at zero mismatch. And what we mean by mismatch is even with zero sort of random fluctuations between transistors, you will get some systematic offset just due to, and we'll do a few examples, different resistor sizes and things like that. And then two, we'll have the random component, and this one will be due to mismatch. Let's say VTH 1,2, and that will then affect the GMs, etc. It could also be W over L, etc. Okay, so let me give you a simple example. If we take a look at our usual resistively loaded diff pair, so let's consider a few examples here. So we have, let's see what happens with this circuit when I have, in general, RD1 and RD2 instead of just having the same exact load resistor. Right. I'm not even saying that M1 and M2 are completely matched, just trying to see what happens at this output if I have two transistors that are coupled and I drive them differentially. So if you look at the output voltage between these two nodes, we're just going to do it by looking at what happens on each branch from VDD. Right? So in this branch, I have a current ID1, and in this branch, current ID2. So I can figure out what this voltage difference is as VDD minus ID1 RD1. And then, so that forms the voltage over here. And then minus the voltage on the other side, which is VDD minus ID2 RD2. Okay. So from here, VDDs cancel out, and I get that this is equal to ID2 RD2 minus ID1 RD1. Okay. So now by definition, we look for V offset as VID for which VOD equals 0. Right, so this is our goal, to figure out what is the input voltage that's required to make the output differential voltage equal 0, no matter what sizing or what mismatch we have in the circuit. So we apply this over here, we're getting this condition that ID1 RD1 actually has to be equal to ID2 RD2. So the ratio of currents is kind of the opposite of the ratio of resistors. Right, so ID1 over ID2 is RD2 over RD1. And that will have some implications in terms of if mismatch if one resistor is larger than the other, then the currents have the opposite kind of ratio, right? So your delta contribution to the mismatch will be negative. Okay, but from here, we can now go and write the current equations and say, well, okay, my input voltage will be VGS1 minus VGS2, and that is VTH1 plus VOV1 minus VTH2 minus VOV2. So now we get the first factor, we get our delta VTH. Well, this is VTH1 minus VTH2. So that could potentially be the mismatch factor. Okay. Then we also have VOVs, and we know that this is sort of 2 ID1 over K prime W over L1, right? And then this one over here will be square root 2 ID2 over K prime W over L2. Okay. So from here, we actually have the two overdrives are a function of IDs, but we already have a relationship between the currents which gives us the offset condition, right? So we're going to just plug this in and then say that, so VOS will be equal to this, and then delta VTH will be plus, and then we're going to just replace ID2 with RD2 over RD1 over RD2 ID1. So we'll write 2 ID1 over K prime W over L1. And then in the bracket, we're going to have 1 minus RD1 over RD2. Now, notice that for this, I at least assume that WL1 equals W over L2. Okay. So I really just looked at, okay, what's happening if RD1 is different than RD2. So this is my only, so this piece over here is delta R over RD2. Okay. If we keep this general piece and just say that here ID2 is ID1 times RD1 over RD2, then we can go and derive a more general expression. Let me just give that. So if we incorporate then we can get a very similar expression. The book sort of goes into detail with this, but if you like to do like Taylor expansions and kind of things like that, you'll get the same expression. But it's essentially V overdrive over 2 times, and then we have here minus delta R over R, which is kind of the same that we had previously. And then we just add minus delta W over L, or W over L. Okay. So what you're going to have here is that delta VTH is usually different because of process variations. So these are random dopant fluctuations in the channel. But also more in recent technologies, there's a very big dependence on layout. And the reason is that all transistors sub 65 nanometer have strain in them. So the channel is strained in order to enhance the mobility. And that strain depends a lot on the patterns around the transistor. So if you go and put just a different pattern in the layout around a particular transistor, even though they're exactly matched in size, you will have a different threshold voltage. And that effect is actually now kind of starting to be much more dominant than, let's say, random dopant fluctuations, things like that. Delta R, this is, again, really just the process in which we're projecting on delta when the mask is done, like what the fluctuations in mismatch around the resistor pattern. And then here is both process and then, as we said, like the layout because of the proximity effect. So depending what's around, you will have dimensional variations as well. Okay. Let me give you a simple example for the one above, just so you can see some of the trade-offs. So let's say we have VTH1 minus VTH2 is 10 millivolts. Okay. That means that VGS minus, and we're going to define VGS minus V threshold, of course, as our V overdrive. And let's say I've picked the situation such that that's around 500 millivolts. Okay. And let's say that I have mismatch or in ratio of these two resistors that we're loading the diff pair. As, let's say, oops, I'm going to say like this. So this is 2% mismatch. This is actually really, really good for integrated circuit processes. Usually you would get like 5 to 10%, maybe sometimes 15% mismatch in poly resistors. So they're not really a good kind of very precise piece of passives to put in the process. That's why we end up kind of loading everything with actives, if you will. But here you get 2%, which looks pretty good. But then if you go and look at the offset formula, we have our 10 millivolts from the difference in thresholds, plus we have V overdrive multiplying 1 minus RD1 over RD2. So this would be like this 2% error. So this would give us, I'll neglect sort of what the sign is here. I'll assume it's 2%. But essentially gives us 10 millivolts, and this piece is actually 20 millivolts. Sorry, that's 10 millivolts as well. So the total is 20. The important piece of information here is that this over here started being as important as the threshold voltage, because a very small error in the resistors was sort of amplified by this overdrive voltage. Okay. So here you see, so there is a trade-off between accuracy and speed. As we said, if you looked at the kind of the FT of MOS was dependent on the overdrive voltage, right? So if we wanted to have a faster transistor in MOS, we could actually affect it by the overdrive. And so here, if we want a faster transistor, our overdrive, we would like to be higher. But a higher overdrive would sort of multiply up the imperfection in the load resistors. So you will get more offset for higher overdrive. So this is a trade-off between accuracy and speed. Okay, so let's take a look at some of the other issues that the offset or this mismatch causes. VOS is sort of the static manifestation of the imbalance of the mismatch, right? Because that's the DC voltage effectively that got shifted at the input. But there's other implications. So if we take a look at our diff pair, there are also implications on these two values, which are, we said that in a well-balanced circuit, the gain between differential mode and common mode and differential mode was 0. Simply because everything was kind of nice and symmetric, right? But here where the two transistors can have slightly different GMs because different currents flow through them, or the two load resistors are slightly different, all of a sudden I start getting, let's say, common mode output coming from the differential input. And I would get also differential output coming from common mode input. And these are very important things because that's how kind of the, let's say, common mode supply noise would manifest itself in your differential signal if you had some mismatch like this. So let's just take a look at a few expressions here. So if I'm looking at the VOD, which is here, for VID equals 0, that means my input is just VICM, right? So I have here VIC plus VID over 2, and then VIC minus VID over 2. Right. Then since I'm calculating the output to this stimulus, I'm going to use the half circuit that corresponds to the common mode input, right? So I'm trying to calculate what happens with the circuit with roughly, I get 2 VICs on each side. And of course, I will still have the 2 RSS in the tail. So my gain will be GM1 RD1 over 1 plus 2 GM1 RSS, right? And this will be times VIC. But I also have to have a component that is the other side, which is GM2 RD2 over 1 plus 2 GM2 RSS. So now I'm going to do something that's, I'm going to assume it's kind of just approximation, but turns out it's a pretty good one. I'll assume that the changes between these two is the same, so I can have the same denominator. I'll call it sort of the averaged GM. And then, but at the top, I'll just keep the difference. This is actually plus into RD2. So now what I have is GM plus delta GM times R plus delta R. So that's on one side. And on another side, I have minus GM minus delta GM plus R plus R minus delta R. So if you multiply this up and kind of cancel out the second order terms, which are, for example, like delta R times delta GM, so that's too small, what you get is something like this. We can label this as halves, just, and then they add up. So 1 plus 2 GM RSS. Okay. So now you see that essentially this VOD, and we'll say VIC here. We'll say that a common mode to differential mode equals this, and also equals to VOD over VIC for VID equals 0. Right? So this essentially depends on the delta in R and also delta in GM. Delta in R and delta in GM are actually the opposite kind of polarity, but delta GM is kind of damped by the kind of the square root of the current, because the delta in current and delta in R are kind of linearly proportional, right? We said that the current times R has to balance on both sides, right? That was kind of the first thing we derived today. So this is still kind of a non-zero component. Now, if you take a look at this whole model, the way we use the half circuit, we said essentially you have VIC, and then in one branch VID over 2, and then in another branch minus VID over 2. And that drove two half circuits and then produced VO1 and VO2, right? And so VOD would be VO1 minus VO2, and VOC would be VO1 plus VO2 over 2. That was our half circuit approximation. So we're still assuming you can cut in half circuit because the perturbation is small, but then the difference in the gains would cause all these problems, right? That's an approximation because normally the slight perturbations you can't actually cut the circuit exactly in half because the two halves are not exactly the same, right? Now, if you look at this approximation over here, we can also go for the differential to common mode. Okay, and in differential to common mode, we get VOD for VIC equals 0, or get VOC. So in this case, this is VO1 plus VO2 over 2. And then you can take a look at what VO1 is. So VO1 is our A1 times VID over 2. And then the other one is A2 times minus VID over 2. So this equals to A1 minus A2 over 4. So that's the proportion of ADM to differential mode to common mode. If we take a look at the differential pair, I want to come back to this so that we're sort of tied together the differential, common mode, mismatch, offset type of imbalances. But as we're going to move on next to sort of more of a frequency analysis, compensation, all these things that you're doing in the lab, I want to sort of also go back to diff pairs and look at the DC biasing. So some homework has kind of some questions on that, but also it will be useful for you in the lab to see how to bias the circuits for different conditions. So if we have our diff pair, and let's say, usually I'll realize the current source as, let's make this VSS, as some transistor. In this case, I'll just use one bias transistor. And then here I'll use a current mirror. Let's say M3, let's say M4. Okay, let's take a look in this situation. What is the range of VIC? And then we'll also take a look at what's the range of the output that I can achieve, so that I can get this circuit to be in the desirable region of operation where I can actually get some amplification going. So what do people think in terms of VIC? What is the range at which we want to operate this voltage VIC? What is it constrained with? In an amplifier, we want to keep transistors in what region of operation? Saturation. So we must be constrained by some transistors staying in saturation region. And given that VIC is first hooked up to M1, okay, maybe we can write out first the condition for M1 being in saturation. Right? When is M1 in saturation? What? So VGD is less than V threshold, right? Okay. So we'll say that VIC has to be less than some value, right? And that's this voltage over here plus V threshold, right? So what is this voltage over here? That's VDD minus VTH4 minus V overdrive 4, and then plus V threshold 1. Right? So we go down by a threshold and an overdrive because this guy's diode connected, and then we go up by the threshold of this transistor. Right? That's as high as VIC can go. If it goes slightly higher up, the gate will be higher than this voltage here by more than a V threshold, right? And will fall out of saturation. Okay? Notice that I haven't analyzed M2. Why didn't I analyze M2? So we haven't looked at what's the swing on this node, right? We will have a chance to analyze that. But normally, this VGS is kind of more stringent requirement on the VIC, right? Okay, so which other transistor is problematic? For the input common mode? M5. What is that? So VIC has to be what? Greater than what? VOV5. Okay, well, let's see. Let's track out the whole voltage loop, right? So we start from VSS, and so we have to do VSS. Then we have to give V overdrive to M5. Right? Then we're at the tail, and then we have to give for the VGS for M1 and M2, right? So this is VTH1 plus V overdrive 1. Right. So this is our total. Okay. If we have a current source that's more complex than just a single transistor, M5, then we'll have to pay larger price on the overhead. For example, we had these two V overdrive type current sources, right, that had a fix for the systematic gain error, where in that case this would be 2 VOV. Okay. Now let's look at the output for VO. What constraints do we have? As how far down can the VO go? Let's say this is VI1, this is VI2. So how far down can VO go? So VO min has to be greater than what? Which transistor is going to be critical? M2. So VO min is VI2 minus VTH2. Now, VI2, is it min or max? What's the relationship between this input and output? As one is increasing, what is the other doing? Decreasing. So it's a pi phase shift, right? So this is max. If there's a lot of gain, I can assume this is kind of very close to VIC. But if the amplifier doesn't have a lot of gain, and I'm applying a pretty big differential voltage, I have to take that into account, right? So what other transistor may be problematic? M3. And this is VO max can go how far? How far can I take this node? What is the acceptable VDS voltage for this transistor over here, so that it's still in saturation? I have a V overdrive plus VTH here, and then this node can pull up by VTH more, right? So what's left? V overdrive. 3. And then we're going to have actually, because we're in absolute voltage, we're going to have VDD minus V overdrive 3. Okay. Okay. So similarly, if we have the cascode load, then instead of looking at kind of just the VDD, you'll be looking at kind of intermediate biases, and then again calculating these conditions. With respect to the gate voltage, you'll be by a VTH up or down, and then also you'll have the same issues in the tail, right? Okay. Okay, so we're going to move now into sort of the second part, which is the frequency response of diff pairs. In many ways, this is very similar to what we've already done, so I'm going to go pretty quickly over it with just noting some differences. Again, for amplifiers, like any linear system, as long as they're linear, you have kind of the transfer function J, and then 1 minus S over Pi in I to NP NZ, or NP is greater than NZ. So this is, and it's always going to look something like this, depending on the number of poles and zeros that we have in the system. So for the amplifier that we looked at, and we're going to first look at the balanced diff amp. Right, same circuit. Now, in this case, I'm going to include also RS, and you'll see in a minute why that's important. This is the source resistance. Every source that I'm driving this circuit with will have some Thevenin resistance, right? And so that will, because I'm driving some capacitance in the gate, whatever's being seen at the gate, I need to take this into account because that will be my first kind of filter or frequency selective circuit that I will encounter. All right, so unless I'm driving it from an ideal voltage source, which doesn't exist in reality. So I'll say I drive, just to look at the differential output, I'm going to drive with VID and minus VID over 2. And so what type of circuit can I analyze this with? How do I simplify this topology? Half circuit, because everything is symmetric, right? So I can go and say, because these are differential, this node is actually grounded. So I'll have this topology over here. Okay. So what is this topology? We sort of already did this, right? It's a common source. And so I'll just real quick jot down. So from this, we get a common source, small signal. And in that one, we had VI, we had RS. Then we had the CGS cap with VGS. Then we had CGD. We had GM-VGS, and then we had here, let me just, CDB, we had R0, and then we also had our RD, and we neglected R0 because RD was typically much smaller than this. Now, when we did the analysis, we sort of also neglected CDB. And then what we were getting is that the DC was pretty much minus GMRD. It would be in parallel with R0, but it doesn't really matter. This circuit, as we'll see kind of later when I derive it a little bit more exactly would have a right half plane 0 that will be GM over CGD. Okay? And if you take a look at this piece over here, that means that since CGS is much greater than CGD, that this magnitude of Z1 will be much greater than omega t, which we had as CGS plus CGD. Okay, so this 0 is pretty far away. But as we'll see, it will, in MOSFETs, MOSFET amplifiers, it will cause some issues simply because GM is not that large, right? So it's not that far away, like, for example, in bipolars. Okay. The other poles we did with open circuit time constant or 0 value, and that P1 was minus 1 over RS, and we had CGS plus CGD times 1 plus GM RD. Right. And if you did short circuit time constant, because this was a 2-pole system, then you would get P2, which was, okay, I'll just write it up just as a reminder, plus 1 over CGS, and then a whole bunch of factors, 1 over RS plus 1 over RD plus GM. Okay. If you take a look at this factor, GM over CGS, that is also omega t, right, approximately. So what this meant is that the magnitude of P2 is also greater than omega t. So here we have a situation where if we draw the omega axis, or in this case I'll just say, okay, this is a sigma, then we'll have a Z1 over here, P1 will be over here, and like P2 will be somewhere over here. If we look at the gain times the bandwidth, this is kind of an interesting property. We had GM-RD, which was the gain. And then if you look at the bandwidth, we're really multiplying by the pole 1. And in the pole 1, I'm assuming that the Miller effect is actually pretty dominant. The CGD, GM-RD is really the most dominant factor. So we'll get RS times GM times CGD times RD. So GM, RD, this is all going to cancel out. And then we have something that is just proportional to RS CGD. So you see, there's no on RD. Okay. So this is in case dominant. So Miller effect, or the factor GM, RD, CGD has to be really dominant for this to be the case. We're going to do now sort of a more general case where you're also heavily loaded at the output. So you'll see that that moves things a little bit. There you can do something with GM to overcome that. But at the point where you're not, so to speak, self-loaded, meaning that you're really dominated by the Miller, then you have this issue. Okay. So this was the differential response. Let's take a look at the common mode. So for the common mode, we will use a different half circuit. So let me first draw this one for completeness. Now, here, I have to include a few other things that I didn't draw in the previous case, because in previous case, it didn't matter what's really in the tail, because in differential mode, the tail will be grounded. Right? Here, it sort of matters. So I'll have my ideal current source, let's say I tail. I'll also have some R tail, which is the resistance, output resistance of this current source. And I'll also have C tail, which is kind of the, in this case, I'm showing just the output capacitance of that same source, right? Or if there was a wire going between the source and the real tail transistor, so that piece of interconnect would also kind of come into play here as capacitance. So if we now go and do the VIC on both sides, we can still do the common mode half circuit here, right? And in that common mode half circuit, we're going to get RD. And then here, IT over 2, 2RT, and then, oops, sorry, CT, the capacitor will be CT over 2. All right, so I've just split all the conductances. So what we're going to assume now is that CT dominates all the capacitances. And usually that actually is a really good assumption, because that tail node will be kind of the most loaded from the source, from the interconnects at that point. And this is kind of something that you really need to pay attention when you design your differential amplifier. So if this is the case, then I can treat this whole thing as just like some impedance that loads my source-degenerated kind of stage. And I can assume all other capacitances haven't actually kicked in. So 1 over omega C is like pretty large on all the other capacitances, right? So I can still use my like DC analysis, so to speak. So to say that a common mode of S is just VOC over VIC, and that is going to be minus GM RD over 1 plus GM ZT. And ZT will be my impedance over here. This is my ZT. All right. And since GM ZT is going to, in the region where it's large, I can approximate this as minus RD over ZT. Right? So ZT will be 2RT in parallel with 1 over S CT over 2. Right, so this will be 2RT over 1 plus S CTRT. So if I plug this back over here, then ACM is approximately going to be minus RL over 2RT, and then we have this term. This is a 0 in the transfer function. Right? And this is actually kind of bad, okay? Which is bad. Mm-hmm. Sorry, RD. Keep interchanging. So RD, RL, yeah, the load. So thanks. So why is this bad? Can people say? Well, zero means that at some frequency I'll actually start ramping up, right? Or my frequency response looks something like this.
say this is log omega, right, at some frequency which is 1 over RT/CT, that's my 0. On a 0, in my frequency plot, I'll start having actually 6 dB per decade up, or 20 dB per decade, or 6 dB per octave. So this is 20 dB per decade up. It's just the gain is actually, the common mode gain is increasing, right? This is up until the point where we start getting all other caps to kick in, right? So there's all these other caps that will kick in and essentially give us the 2 poles that will shave it off, right? But before then, we were going to get to this 6 dB per decade increase in common mode gain. Now, why is that bad? Well, this, we said CT is actually pretty large, much larger than CGS and CGD and all these other caps. So this, and RT is also pretty large, right? RT, we wanted to make it pretty large because that's the output resistance of our source, right? So this is actually relatively low. And if you look at the ADM, which is the differential, that one will have something like this. We'll go, and then somewhere before all these kick in for the common mode, it will start rolling down, right? And this over here will be our P1 that we did. So this would be approximately 1 over RS, RD, GM, CGD, right? So if you look at this region over here between the two, what's happening here is that differential mode is staying constant, common mode is increasing. So what's happening with my common mode rejection ratio? It's going down. So this is, and it's still within my bandwidth. So this is where things are still useful for me differentially, but I have more sensitivity to common mode, meaning supply noise, all the other stuff. And unfortunately, supply noise and all these things are all high frequency anyway. So this is actually the region where we start having problems. So if you take a look at the common mode rejection ratio, which is ADM over ACM, then you start getting something where we're pretty good up until this point over here. And then we start getting minus 20. And then after the bandwidth, of course, we get minus 40, or okay, let me write it so that it's a little bit more. So minus 40. Right. So this region here is problematic. Okay. So for next lecture, we're going to look at the a more detailed analysis for the same stage. Essentially, it's a common source, and see how this CC or CGD cap has sort of a bigger role than just the parasitic cap. We'll see how without it, you sort of have the 2 poles that are close to each other, which is the input and the output pole. And then with it, these poles actually move out. And we're going to use that feature to add a lot more CC cap to be able to split poles and start doing something that's called compensation in the amplifiers. So for the next lecture, we're going to do compensation and also explain that a little bit more. That's something also you'll be doing in the labs as well. Okay.